Welcome to the very first episode of History and Apparatus, where we will concentrate on significant technical and mechanical archaeological findings that help us understand the scientific achievements of the ancients and their contribution to mankind's evolution. In this episode, we will be talking about the Minoan solar calculator, a vastly old non-automatic computer, how it worked, its use, its contribution to seafaring and planning, and the mind-boggling high level of knowledge of astronomy and the works of the solar system itself. But before we talk about this extraordinary device, let's get acquainted with the Minoans, the people of King Minos of Crete. What historians today call the Minoan civilization is the archaeological findings of the remains of a network of Greek cities and ports that flourished during the Bronze Age in the Aegean Sea and the Mediterranean. With the island of Crete as its center, the people of Crete expanded their reach all over the Mediterranean and possibly beyond. They flourished from 2700 until 1450 BC, where a period of decline finally led to the end of their achievements around 1100 BC. There are strong indications and evidence, both physical and cultural, as well as historical, that they are related to the Mycenaeans, the other great Greek civilization that was active in the mainland of Greece during the same period, whose center were Mycenae, Tiryns and Tyre, a few tenths of miles north of Crete, in the Peloponnese Peninsula. The Minoans are perceived as the first truly advanced civilization, the oldest on the European continent and one of the earliest on the planet, leaving behind massive building complexes, with running water and sewage systems, elaborate tools and devices, methods of industrial production, stunning artwork, writing systems, and a massive network of trade that might have reached even as far as the heart of America, where they could have possibly mined and brought copper for trade. But more about the Minoans in another episode. Back in 1899, near a town called Palaeokastro on the island of Crete, there has been discovered a curved stone with embossing symbols on the surface that are associated with the sun and the moon. Dating of these molds were an open subject until recently. The common predictions was between the 1500 to 1600 BC, but in 2019, Professor Jan Velsink dates them with accuracy between 1850 BC to 1700 BC. In 2010, after acquiring a permission from the Heraklion Archaeological Museum, a team took high-definition photographs of the device, with a magnification of about 5 times. Upon examining the magnified photographs of the disk, the team observed that there were various depressions, dots and notches in numerical ratios that indicated a relationship to astronomical phenomena. The most obvious interpretation would be an eclipse calculator, which could be produced by imprinting a copy of this mold on a soft solid, for example, malleable metal or even on soft wood. The team also has constructed a 3-dimensional model of the Palaeokastro disk, with its original dimensions, which is 8.5 centimeters by 8.5 centimeters. Now, we will take a closer look of the ray-bearing disk. In the disk's circumference 25 triangular rays, or teeth appear. Out of the 25 triangles, 20 have 5 tiny dots, 4 have 3 dots, and 1 with only a dash line, probably being a starting point. The total number of these dots is 112, which makes it an astronomical discovery, since the Soros cycle consists of 223 lunar months. Now you are probably wondering, what is Soros? Soros is a chronological period of 223 lunar months, approximately 6,585.32 days, or 18 years, 11 days, and 8 hours, which is used to predict the eclipses of the sun and the moon. Knowing a Soros cycle is 223 lunar months, 112 seem to be too close, and not a mere coincidence for that number to be half a Soros cycle. A different way of expressing this is to divide 112 by 6, getting that approximate number of years of a Soros cycle, which is 18.66. Until now, The earliest record of the Soros cycle comes from Babylonian astronomers from 750 BC to 1 BC. But this finding predates the Babylonians by almost a millennium. On the disk, there are 2 engraved circles, the outer containing 58 small circular holes, and the inner one, a single depression containing 59 carved short lines, which are interrupted in 4 places by a cross. The 2 lines of the crosses we see here are sectioned vertically and horizontally. The vertical line has 11 markings in its upper part, and 10 markings in its lower part. The horizontal line have 2 rows with markings like dots, the upper row on the left, having 10 markings, and on the right part 7. The lower row has 11 markings on its left, and 8 markings on its right, making a sum of 19. The horizontal width of the cross divides the disk into 2 semicircles, each of which has 28 dots. It can be observed that, if metallic imprints of this mold are created, then, in addition to the disk, there will be 2 pins, each 6 centimeters long, and a flexible tweezer-shaped object that probably served as a gyrocompass, probably for drawing circles and measuring distances. After numerous tests, the team came to the conclusion that this small device has a multiple purposes apart from the use as an eclipse calculator, and with the use of a pin placed at the center of the cross, its solar shadow on the disk's surface could lead to the determination of the following elements. The true solar time during daytime uses a sundial. Usage as a geographical latitude finder or compass. The cardinal points on the horizon. The first day of each of the year's seasons. These probable functions of the disk will be presented next. Now we are going to analyze the disk's use as a sundial. The mold imprint can determine the hour and the geographical latitude of a location, with the use of the 3 tools included, which are the 2 pins and a pair of a concentric gyrocompass that we see on the mold's right side. The disk has 25 triangular teeth, if they are counted per half-hour intervals, and a pin is placed perpendicular to the central cavity, then the pin's solar shadow cast indicates the point of the disk's perimeter that corresponds to the time of the observation after aligning the disk's central cross in the north-south direction. In this way, this simple device could be used as a portable sundial of 12.5 hours. Its hour corresponds to approximately 58 minutes, very close to the modern hour. The triangles, rays or teeth, are not of equal size. This could probably be related to the fact that in antiquity the hours were of unequal length, with each tooth corresponding to approximately half-hour increments. The dots on each tooth divide this length of time into 5 smaller time intervals, about 6 minutes each. Usage as a geographical latitude locator. By looking at the device in the use of a pin and a pair of gyrocompass, with the user marking every 14 or 15 days the edge of the pin's solar shadow at the moment of the true noon, then within a year, a shadow cast would form. A figure similar to the digitators we see here. The shadow's angle at the equinoxes is at the 2 edges of the crosses we see on this image, and it is equal with the geographical latitude of Knossos, approximately 35 degrees 15 minutes north. If a user had marked the shadow lines in the area of Knossos for a whole year, and then traveled to a location in the north, for example latitude 51 degrees, he would be able to find the latitude of the new position within half a month without prior knowledge of the date of the year, just by comparing the 2 shadow casts. Using this method, and marking the pin's shadow in 15-day intervals, while traveling back to the south, the user would know that he was at the same geographical latitude with Knossos once the shadow produced the same shadow cast as the initial one. It would be easy for him to then return to Crete by sailing east or west. This small device with multiple uses has another astonishing function, that of a portal analog calculator, predicting lunar eclipses. The device records every eclipse that occurs, per lunar month and year, whenever the Sun and the Moon are in conjunction, in other words for every full moon, or at the new moon phase near a node of the lunar orbit. What is a node? To understand this, we have to imagine the Earth's orbit around the Sun, and map out a 2D plane that is referred to as the ecliptic. The Moon does not orbit on the same plane, it is tilted by about 5 degrees. This means that most of the time the Moon passes above or below the Sun, as seen from the Earth. We can map out two invisible points in space, which the Moon's orbit crosses the ecliptic. Those are the lunar nodes. When they line up with the Sun, Earth, and Moon, that is when a solar eclipse or a lunar eclipse occur. This is referred as the eclipse season, and happens about twice a year. The Sun travels on the ecliptic at about 1 degree a day, and has a good line with the node about 36 days, 18 days until it reaches the center of the node, and 18 days after passing it. The Moon reaches this specific node every 27 days. The nodes are moving in the opposite direction of the Moon's elliptic orbit, and they make a full cycle within 18.6 years. Another extraordinary observation from the Minoans was that the disk's rays represent the node's 37 degrees line of sight, from the Earth's perspective as we see here. Coming back to the device we see, the inner circle is divided horizontally by a double row, into two semicircles, the one with 29 carved dots, and the other with 30, with a total sum of 59 dots. These two inner circles, with the 29 and 30 dots, led to the conclusion that they correspond to two successive lunar orbits, apparent orbits since their average is the number of days in a lunar or synodic month. That is the average time between two successive full moons. The exact value is 29.53 days, a difference of only 44.05 minutes per month. To use the die as an eclipse calculator, 6 pins are required, corresponding to the following positions. 1 for the position of the Sun, which moves counterclockwise, on the outer circumference with the 58 dots, 1 position per approximately 6 days. These dots are numbered with yellow. 1 for the position of the Moon, which revolves on the inner circumference with the 59 short carved lines. These lines can be seen here with the green dashed circle. 2 pins for the nodes of the lunar orbit, that are placed opposite from each other, on the 112 dots that run along the edges of the triangles. The team also discovered that the nodes move 1 position every 2 lunar months. Hence, the nodes can shift by 6 places every 12 lunar months. And the final 2 pins are placed on the dots of the cross, to follow the number of the lunar months, and the years that pass. The months are on the horizontal arm, and the 18 dots for the years are on the vertical arm as we can see here. With such a device, the astronomers of the Minoan period could predict with considerable accuracy and precision the lunar eclipses, as well as some of the solar ones. For the disk to function as a lunar calculator, first of all, the device needs an initialization. This can be done after a lunar eclipse, preferably a total one. Each day corresponds to the advancement of the Moon's pin by 1 short line in a clockwise direction, along one of the 2 semicircles of the inner circle shown here. In other words, the number of days after which the Sun's pin moves by 1 place is the result of the motion of the Moon's pin with the sequence as we see here. In this way, the Sun moves by 56 positions in the course of 1 lunar year of 354 days. Every 2 lunar months the Sun moves by 9 positions, and after 177 days or 6 lunar months the Sun will have moved by 28 positions. A total or partial lunar eclipse occurs when the Moon is full, and at the same time the Sun is near one of the lunar nodes. When the Sun is very close to the point of the node, a total lunar eclipse occurs, while when it is just close to the node, the eclipse is partial. The initial conditions when the calculation starts are from the total lunar eclipse which happened the 21st of December, 2010. 7 days later, the Moon has moved by 7 positions, while the Sun has moved by 1 position to the opposite direction, according to the 766 sequence, 15 days after the total lunar eclipse. Now the Moon is full, and the Sun has moved by 2 positions to the opposite direction. Since we have full Moon and the Sun is close to the node, a partial solar eclipse is observed, in the 4th of January, 2011. Here, we observe the positions of the Moon, the Sun and the nodes 2 lunar months later, on the 23rd of February, 2011. Similarly, the positions of the Moon, the Sun and the nodes, 4 lunar months later, on the 24th of April, 2011. Observing the positions of the Moon, the Sun and the nodes, 6 lunar months later, on the 15th of June, 2011, the disk predicts with accuracy this eclipse. On the mold's left-hand side, the team observed a jar-shaped object with the carved symbol of a cross, as well as 18 dots in the form of a cycle around it. On the outer circle there are 28 dots, with the lunar symbol in the form of the crescent moon. This leads to the conclusion, from the coexistence of symbols of Sun and Moon, as well as the 18 and 28 dots, to a Soros cycle. That means, within a Soros cycle of 18 years duration, 28 lunar eclipses occur. On the opposite sides of the Moon symbol, it might be Mercury and Venus, because they perform the same journey with the Moon, during the sunrise and the sunset. Beneath these celestial bodies, the large circle probably represents the Earth, since in the sky of the Earth the 28 lunar eclipses in 18 years can be observed. As a conclusion, it can be said that the device generated by the mold of Castro can be used as a competent lunar and solar eclipse calculator even to this day. During the research, the team started at a known eclipse of the 21st of December 2010 and tested until the 31st of December 2028. As for its accuracy, in a total number of 33 eclipses, only 2 are not predicted, giving a 6% error, while 94% of the predictions are accurate, in a duration of a full Saros period of 223 lunar months. However, a solar eclipse may pass unnoticed for a civilization not possessing the proper equipment. That can happen with some partial or annular eclipses, or because it is not visible from the Mediterranean if the path is on the other hemisphere. Therefore, the device would probably have been used primarily as a lunar eclipse predicting device, in addition to its simpler uses, as a sundial and a geographical latitude finder. The Castro mold can be regarded as an integral part of the astronomical knowledge of the Minoans, as it is evidenced by the astronomical orientations of palaces and sanctuaries that have been determined by archaeoastronomical research. Thanks for watching, and if you want to see future videos, please subscribe and click the notification button. On the next episode we will talk about the Minoan eclipse calculator and its relation with the Stonehenge. A special thanks to Dr. Tsikritsis that helped us during our research of this subject. For further details about the Minoan eclipse calculator and references, please check the description below.